didn't really expect to be on the first talk on the big auditorium. Quite an honor, thanks. This was meant initially as a kind of mix of the presentation and above. So let's say it's going to be a not too long presentation, and we will have plenty of time to discuss at the end. And the point today is discuss debugging GPUs and how we can do that in GDB and mainly in upstream GDB in the future. So to do a quick, overview of what you have available if you want to debug something running on the GPU today. Not a lot in upstream GDB, but most vendors do have a downstream port of GDB. So AMD has been working on Rock GDB, which is the downstream version of GDB for AMD GPUs. Intel has been working on GDB 1 API, which is a downstream version of for Intel GPUs, and NVIDIA has CUDA GDB for CUDA GPUs. And obviously, 3 projects, 3 histories, different choices in many of them. So I kind of feels different if you use one or the other. That's how it is today, and we'll see where we go. As far as upstream GDB is concerned, so there is support for AMD GPU in upstream GDB today. Might have been available since GDB 16 or so, but it's still quite very basic and bare bones. And everything we're going to talk about today, which you kind of need if you want to have a meaningful debugging experience, is not available for reasons we're going to explore. And Intel has also started to upstream, some of their work. It's still currently under review on the mailing list, so I guess it's also a call for the maintainers to go and continue the discussion on that series, so that can land and we can have support for 2 families of GPU in the upstream GDB. And so, as I said, currently we have mainly 3 downstream versions of GDB. 3 kind of differences. And one of the problems we've been facing when trying, starting the upstreaming is, okay, we can do, many of the backend stuff because it's going to be quite independent, from one GPU vendor to the next. But there are some GPU-specific, concept and consideration that do impact the user interface, which are handled differently in the various downstream. And so before we can do anything upstream, instead of having a race of who's going to upstream first and so choose what the interface is, we kind of all convened and agreed beforehand that let's not do that. We can submit the backend, and we need to have some discussion about how will upstream GDB will handle GPU debugging and what interface it is. So let's learn from the 3 downstream ports, see what we like, what we don't like, and decide what goes for upstream GDB. And that's the task that we started last year at the GNU Cauldron. So there was a buff session. So pretty much, run by Baris here from Intel and myself for AMD. And we started to discuss line supports. And the point at the time was mostly to show what kind of interface, what kind of choices we've made, over the time in the different downstream of GDB, see how they differ, and try to understand, why one company did something, the other did something else, and see, okay, how can we converge to something? So that was the starting point of that collaboration. And since then, we've been meeting regularly, fairly regular basis, trying to iron out a consensus. So we're here just 2 of us presenting, but it's really been like a team effort. A lot of other people from the various team are in the room. Some are not, but it's just not just a 2% thing. And I think we've reached mostly a consensus about the lane debugging part, which is what we're going to present and discuss today. And then we will have more things to discuss in the future. So I guess next year we can have the next part of the conversation. So to address, to understand what we mean by lane debugging, we need to take a small detour by the GPU programming model and understand how do you program a GPU, how is that slightly different from a CPU or not, and see what do we need to show in GDB for that to make sense. And so the classical way to think about programming a GPU is going to be you need to specify your problem like in the space. It can be 1, 2, 3D, usually driven by your data. And from historically, because GPU were for graphics, and the program we run, we tend to call them shader. Like the idea was really you will have a small program which will compute what's the code for that given pixel. You get the XY coordinate of the pixel and go and compute the code for that pixel. And that's why we end up with that model where we define our problem in the space. We write a small kernel that's going to run for each individual item independently on that space. And we run that on the GPU. And one good thing about that and what GPUs are really good about is usually it's mostly independent from one item to the next, so it's massively parallelized. And so, how does that map to actual hardware? On the hardware side, GPUs have big, highly vectorized score in a way, if you want. And so we have kind of hardware threads. So there is kind of a difficulty in terminology depending on who you talk to. You will have a different name for it. If you talk with AMD people, we call that a wavefront. If you call to Intel people, they call that a thread. And if you talk to NVIDIA people, call that a warp. But really, in the end, it's all the same thing. It's a hardware thread. So one unit of execution, you will have one PC, and you will have a lot of big vector registers associated with that. Your vector registers, pretty much as for the CPU, they're split in lanes. So you have, depending on the architecture generation and whatever, you have like 32, 64, 16, maybe some have wide register. So, and each element inside the vector register is going to be referred as a lane. And in the programming model we make it so each element from our model space that we call a work item, which is going to work on one individual element, is going to be mapping to one of the lane of a hardware thread. So at one time, a given hardware thread is going to execute 32, 64 work item at one given time, at a time. And so one of the first things which was not too controversial between any of us was one hardware thread is going to map to a thread in GDB. So when you do info threads in GDB, you actually list all the hardware threads rather than the work item, which is what you would think as a thread when you actually program the thing. There. So how does the execution work? Because you're running on the same CPU, I think 32 kind of programs at the same time, and not really used to that, not in that way in the CPU. And the way it works is, so everything executes in lockstep. So we have one instruction applies to all the elements of the vector register. That part is pretty familiar. But then to handle branching and everything, we use predication. So for your hardware thread, like each hardware thread will have a mask register, which will tell if a given lane is alive or not, active or not. So in that very simple example, like we say, okay, if I is even, just do output I equal I, otherwise output I equals minus I. So the first thing you execute, you evaluate your condition for every lane inside your program, so every one of those 32 work items. That will evaluate to a Boolean, so 0 or 1, and you store that inside your own predication register, where one bit is going to map to one lane, which we pretty much have here. And the effect of that is that will activate or deactivate the set lane. So an active lane does pretty much what you expect, and an inactive lane is still going to execute anything, it just doesn't have any side effect. So it's pretty much like you replaced your instruction with an OOP for that particular instruction. So here, if we execute, we've executed our condition, is I even or not? It's true for 0, 2, 4, 6, and so on. It's false for 1, 3, 5, 7, and the rest. And so when we come and execute our output of I, those I statements, we do have an effect for the odd indices, and nothing happens for the no, we have the other way around. We have something happening for the even indices, and nothing happens for the odd ones. And then when we get to the else, pretty much we flip the mask, because everywhere where we had 1, we want a 0 in the predication mask. Everywhere where we had 0, we want a 1. And then we can carry on and we can continue executing everything. So output of I equals minus I is going to be executed only for the lane 1, 3, 5, 7, and so on. And that's what we have happening here. And when we get outside of that last basic block, we restore the mask to its original value, which was assumed to be everyone is active. That's pretty much the execution model we have. But then that comes with no question when you use GDB. And you say, okay, I'm stopped somewhere in a thread. My PC says I'm somewhere where I is defined, but I'm executing 32 work items at a time. So what does that mean if I say print I? Doesn't really mean anything really, because which one of the 32 I's are you referring to? If you want to think about lane 0, I is going to be 0. If you want to think about lane 5, I is going to be 5. And same when you want to, evaluate output of I, what's the value of I and how do you compute that? So the main task here is the same way we do have, inferiors in GDB, we have threads in GDB. We need to have some bit more element of context that the user can select when you have a given thread. You want to introduce the notion of, okay, what's the current lane that you're going to be focusing on. And that's, like the rest of the presentation is mostly going to be about, okay, how does that impact the UI and the different way you interact with GDB. That's it. Just one note, if we want all of that to work and have a meaningful debugging experience, we need also some dwarf support. So 1 bit is in for dwarf 6, that DW push lane. There is way more to come. We can discuss that at the end, depending on the time we have and everything. So from here, I let Baris walk you through everything we've been discussing, what we think is a reasonable interface for upstream GDB that will impact at least all the vendors that want to upstream their work, and we'll see maybe it will impact other vendors. Who knows? And Baris.
Thank you. Hi. So what we are going to see next are, well, this is actually the consensus that we have arrived at. So there will be some proposals from our side, I mean from the consensus of 2 vendors. So what kind of changes do we want in GDB in order to support lanes? This is mostly about maybe adding new commands or changing the existing commands in order to have this support. So let's start with the basics. Before I say a few more words about this, one motivation that we had in this work was, okay, so GDB has already some commands, some kind of user experience. I mean, there are a lot of users there who are accustomed to the existing way of doing things in GDB. So one of the main motivations we had was, how can we extend this existing user experience naturally to these new commands or a modification of the commands and the user interface. So today, in existing GDB, so you can switch to an inferior or you can switch to a thread. So an inferior means, well, basically if you are debugging a core file, for instance, it's the core file, or if you are debugging a live process, it's the process. And then you can also switch the thread. So this is how the user changes the context. And to be able to do the switch, the inferior command takes an inferior number. And the thread command also takes the thread ID. The thread ID is inferior number dot thread number. But there's also a version where the user can omit the inferior ID. In this case, it means current inferior. So the current inferior in this case is implied. Now what we would like to have is a new command, a lane command, which is going to allow the user to switch the lane context. And the lane, for this, the parameter here is lane ID, and lane ID is a triple. Inferior number dot thread number dot lane number. Similar to the thread command, the user may omit, as a shortcut, as a convenience, the inferior number or the thread number. In this case, current inferior or the current thread is implied. When the user executes the inferior command in order to switch the inferior, what GDB does today is prints an information message saying we are switching the inferior, and then also another message saying that we are switching the thread. With the addition of lanes, now there would be one more line here, switching to lane, where GDB tells the user, okay, now this is your new context. If switching the thread, today GDB says switching to thread, and then it gives you the frame information. Now with the existence of lanes, there would be an additional line here which says also switching to lane. And when the user switches the lane with the lane command, then there would be an informative message. You take a look at cursor, right? No, I was trying to get the pointer cursor, but okay, let me use this one. If you take a look at these lines, switching to inferior, thread, and lane, there is this information about the process. So there will be a target ID printed for the process in the first line. This is what the target says about, I mean, what process this is. For instance, it could be the process ID or some other kind of an identifier. It's defined by the target. And then for the thread, there will be another identifier that's defined by the target, and for lane, also another identifier. So the target here is free to choose how to represent, how to give an information about what this is. Remember from the previous slides that Lancelot presented, the programming model, the data space. So there's the thread, and then there's the work item. For instance, as the target ID for lane, the target may choose to give some information about the work item that's being processed by the lane. There are inferior and thread commands in GDB without any arguments. These are just for information in order to show the current context. So similarly, as a natural extension of this, the lane command without any argument would show the current lane context. Coming to the breakpoints, today, when a breakpoint is hit, GDB tells, okay, we are switching to this thread, which hit a breakpoint. Here's the target ID for that thread, and here is the frame information. Now that lane is also a context, we would switch to a lane, not just a thread, but also a lane. So we are proposing that GDB prints this lane information. It tells that you are switching to a lane. But in the second line here, it's again printed that we are switching to a thread. It's because of this lockstep execution. Actually, the thread hits the breakpoint, but then we need to switch to a lane. So you may think of this as all the set of lanes actually hitting the breakpoint all together. So what happens here is that the line here would contain information about which lanes actually hit the breakpoint. And although they are executing in lockstep, there may be a breakpoint condition, and for some lanes, the condition may hold. For some others, it may not hold. So what happens here is that all the lanes for which the condition holds will be reported. And then for breakpoints, today GDB has inferior and thread clauses. These clauses can be used in order to make a breakpoint conditional on an inferior or a thread, which means, for instance, with the thread clause, only if that thread specified by the user, if it hits, then the breakpoint is considered to be hitting. So a natural extension of this is to add a lane clause, and similarly, this makes the breakpoint conditional on the specified lane ID. Another important command here is info threads. So info threads gives you basically a table where for threads we see a bunch of information. It's the ID of the thread, the target ID, and then the frame. Now with the existence of lanes, we are proposing that we add another column here, a lane column, which would be shown if there are threads that have lanes. And the reason why this column is added here is that in the frame information, there are arguments, frame arguments, and the values of frame arguments here are shown from the context of the selected lane. So in order to make this clear to the user, we propose that we need to show the selected lane as another column. And then, like there's info threads, info inferiors, there would be info lanes, which optionally takes a list of lane IDs, and then it presents to the user information about the lanes. If there are no arguments, then it would print all the lanes of all threads, of all inferiors. Again, this is a behavior that we are following that exists for info inferiors and info threads. The information that would be printed is the ID of the lane, its state, the target ID that's defined by the target for this lane, and then the frame. The ID in this example, for instance, what you are seeing is a tuple, a pair, which is the thread ID dot lane ID. If there were multiple inferiors, there would be again the triple lane ID that we saw in the previous slide. The command would take some flags, in order if the user wants to have, the state here can be active, inactive, or unused. Active and inactive is what we saw previously in the part Lancelot presented. Unused means, so some lanes of a thread may be just deactivated even from the beginning when the thread is dispatched, because it may be because the program space is not so divisible by the distribution to the thread lane width, and then some lanes may remain unused, for instance. And then the accepted flags give the user, one moment please, gives the user the ability to print all the lanes or just print active ones or inactive, unused ones, and these flags are additive. That is, if the user says, okay, dash active, dash inactive, then this is going to print all the active ones and the inactive ones. Please. The question is, can you select, for instance, for one thread, can you do, let's say my thread is inferior 1 dot thread 7. I want to display the lanes for that thread only. Yes, this will be possible. Existing in the thread command, info threads command, you can, for instance, do inferior 1 dot star. This will be available in this command as well.
And again, we have like the same implicit, completion of the triple. So if you just do info line star, that means implicitly the current thread of the current inferior, and that's what is probably going to be used quite a bit. So info line star is going to be the go-to command.
Yeah, one of the focuses that we had is there's existing way of doing things in GDB. We should have them as much as possible whenever they make sense, in the way that they make sense. Okay, then there will be some convenience variables. For instance, there is currently $_thread, which is a replacement for the number of the current thread. There would be the lane convenience variable, which gives the selected lane's number. And then there would be lane count, gives us the number of lanes that a computation kernel was compiled for. And then lane used count, this is the number of lanes that a thread was started with. The previous slide, I said that there could be some unused lanes, so it's related. And then some more convenience variables. Going back to the data space thing, I mean, in general, this is three-dimensional, but for simplicity, what we see here is two-dimensional. So this data space could be split into work groups. And within each work group, there are work items. So remember that one work item is processed by one lane. So for that current lane, then there would be one specific work item that it maps to. And this work item has a position in this data space. It has a position in the global data space, like this much away from in one axis and this much away in the other axis. That's the global index of this work item. And then it also has a local index. That's the index of the work group, of the work item within the work group. So there would be convenience variables in order to query the size and ID of the global coordinate. And then for the current thread, which processes a set of work items, this This thread would belong to a work group, and with this convenience variable, it would be possible to query the coordinate of this work group. These convenience variables are 3-element integer vectors. GDB, if you switch to OpenCL, I mean, Pedro pointed this out, if you switch to OpenCL, then these vectors are already defined and recognized by GDB, the vector types, and you can access their elements using the bracket operator, or there is this .xyz notation in order to access the elements of a vector, or even there's .s and then the index notation. So we would like to have these operators, the way to access elements of these vectors. And then also define a printer. For instance, if you print work item global ID, then it prints the 3 elements XYZ in the way that's shown on the slide. Moving ahead, GDB has an interface called the MI, the machine interface, which is less friendly for humans, but more friendly for machines. So the idea is that IDEs, graphical user interfaces, can use the machine interface. It's basically, again, a command line interface. There is already -- thread, which the client can specify in order to set the context of a command. Then there would be a -- lane in order to set the lane context. List features command would announce that now GDB supports the lanes feature. And then for breakpoints, break insert command, which is used for defining breakpoints, there would be -l to be able to define a lane condition. And then in the output of some break-related commands, breakpoint-related commands, there would be a lane field which gives the number of the lane if the breakpoint is lane condition. We see one example here. The breakpoint is inserted conditionally on thread 155 and lane 5, and then the output responds with a definition of this breakpoint, and in the output there is the lane field. Moving forward with MI extensions, in the stop events that are reported by GDB, there would be some optional fields. For instance, the active lanes is a list of lanes that are active in the thread that stopped. Or hit lanes, it's again a list of lanes for which the breakpoint was hit. The lane count and is the number of lanes. And lane ID is the selected lane of the stopped thread. And then there's the var create command. So this is a command that clients can use in order to define some objects, some variables that they want to print. This remembers the context in which the variable was created. Because now lane is a context, the lane ID would also be remembered. There is a prototype implementation in the URL that you see. And Lancelot has a build of this in his laptop. So if you would like to see this in action, we can give you a demo during breaks or other times. The idea is to upstream these, maybe clean up, prepare them for upstreaming, and then send them for review. So, to conclude, so Intel and AMD came together, the developer teams, And I view this as a success, actually. So it's been very, very effective and fruitful. So there's a consensus to add lane support at the UI level, at the user interface level, what kind of changes we want in GDB, new commands. So the consensus is there, and we would like to propose this to the community. Of course, this is the first step. I mean, maybe you can call this version 1, but there's still a lot of stuff to do. I'm sure there will be more details and discussions about what these commands mean, and then how they can be extended to other things. There are things that are not covered yet. For instance, there could be a Python API or a Dial API. And then there are things also related to not just lanes, but GPU debugging in general. Address spaces is an active topic that we are discussing. And then Dwarf 6 is going to have a non-trivial amount of changes that are also focused on providing support for GPU debugging. And the idea, the philosophy that we have from both sides is to upstream everything. And for this, of course, we would appreciate the support and the time that's put here by the community. And Intel's patches are still under review, so we would like to invite everyone, especially the maintainers, for reviews. There will be a GDB BOF tomorrow afternoon. The discussion may continue here if you are interested, but of course other GDB-related topics will be there too. And finally, this is disclaimer from AMD. Thank you for reading it. And this is from Intel. Thank you for reading it too. I will go back to the conclusion slide, and we can have questions. Yeah, that's all.
So I don't know if there is a mic, but we can repeat the question after it's been asked. I don't know if someone in the technical side has a mic that we can use and share in the room. Otherwise, or like I don't mind if you want to pop on the stage and have the question on the mic. Maybe it's as it. So now it becomes a three-vendor kind of presentation. I love the consensus.
Yeah, sure. So, I guess a small comment is that there are some smaller assumptions. I don't see this anything breaking really. But for NVIDIA, for example, we don't really view lanes as parts of hardware. We really represent them as the threads. So, and also the execution mask, it's a bit different. So the thing is, here, I guess my only concern is with the convenience variables. Because some of the convenience variables are really source-based, not logical thread-based, where the lanes are actually logical thread-based, which can't have coordinate source entities on top. So really, this work item, global, local, all of these are source-based. And my only question is, are they actually really tied to the lane concept in the implementation, or they can fully map to a thread? So for example, work item global ID, can it be mapped to a thread? We don't really force it to be lanes. Because here we kind of have two separations, current thread and current lane. And we would like these to be mutable depending on the vendor.
I can discuss that. So I guess the first point is one thing I did discuss very early on, which we have, I guess, a different view of what we map with. So you map work item to GDB threads.
Yeah.
And then the question is, how does that work if you select a thread, like a work item, you set schedule locking on, and you step it, does that break the concept of the schedule locking, where only that one thing that thread that you change?
Well,
Because
I mean, you still have a lock step, but you can step threads, and we will step all the active threads. But the concept of active and inactive is a bit different. So effectively, you can view our threads really behaving as threads. And they are presented as being proper threads. They can basically execute independently. They might trigger that other as well, but there is no such thing like other threads from the same warp or the wave are waiting somewhere for the execution to get. They can actually activate. So they have this independency of the execution. So I mean, it is the only way to model them as the proper threads, not as lanes, as in the case for Intel and AMD.
Yeah, which
They're threads.
is kind of a big difference.
Yeah, but then most of these things don't really affect it. These do.
Those ones are really meant to be per lane for the most part. Which would be per thread if we want to transport that to...
All of them.
Yeah, all of them. For Intel. We can have a version of that's per wave, at least for the AMD hardware that I know. We have kind of a notion that when you have a hardware thread, it's going to be the nth wave of a work group, and you can have some notion of coordinate of a hardware thread, but that would not really map to that, and not really map like the logical view and like the data space.
Like imagine for us, logical view, you actually have threads, but then you also have concept of waves that are not really threads. They're kind of like workloads, effectively. In some ways, not really, but there is like a different levels of entities.
Yes.
But our threads and these kind of things are really for this particular. We don't have a need to expose lanes at all, this manner, but we do have need these convenience variables. Okay, so that was kind of my base of the question. This was the only concerning part, because as soon as you have work items and these kind of convenience variables, as long as they're not really kind of expected or hard-coded to be lane specific, and they can be anything, then then that will work fine. Right. Okay. So that's good. So this slide is more like not correct in that sense. It's correct, right? Right. Ah. Okay. Okay, that's good. Yeah. Yeah, as long as there is no like physical dependency or expectation, then this is all fine. Yeah. Okay. Yeah, that's good. And then this kind of more of my curiosity, just in general way how GDB work. The last slide, when you have the MI commands, the war create one.
This one?
Yeah.
Okay.
So it is for me. It is a bit interesting here, and this is completely different discussions that we had even when I was at AMD, where when you have this kind of war create things, now we are adding later the basic as a context. That for me makes perfect sense. What was always a bit confusing to me when you create like how do you then call them? Kind of like temporary convenience variables in the expressions, user expressions.
Yeah.
They don't really carry a context. So why is there this kind of parallel between how the MI the context dependency of the variable created through MI compared to the user expression. But maybe that's a different story for a buff or a general.
Yeah, that's probably a discussion for later. That at least that's not something that's part of the consensus we've built so far, and we've not really addressed that. So I'd say it's still an open question. On when you create something, set $3 equals something where you create. How does that behave? What kind of information of the context of that were present when you created that carry on? It's still pretty much an open question.
Okay, so I guess we will have to have like a discussion, maybe not really in the dwarf group because it's outside of it, but between the companies to figure that out. Because I think the things in the user expressions made sense while the target was only CPU. So not really carrying the context and just carrying
the use of user expressions versus this war create are different though. The purpose.
But then why they are different? When you think about it, I mean, when you create something in user experience, you change any of the context. That thing actually depends on the context. Currently in GDB, it will just try to find a similar context currently and display it. But that's almost never correct, right? So I kind of draw the parallel here because this kind of makes sense to me. Though the use case, is kind of different, but the logic should be the same. Dependency makes sense. That's the thing, it will not. The end implementation didn't do that. It only remembered the scope, but the scope didn't really remember the context. It's just dependency. What needs to be present as context. No, it doesn't. My implementation doesn't. And that's the one that we agree on. I mean, the original implementation did do that. It will basically remember the whole context, to remember the thread, the process, the whatever. It will actually figure out through the dwarf expression, through all of the intermediate values, even results, it will remember all the context. And that's how I originally designed it. But then we found that that's not really in behavior of the existing commands for the threads. So what we agreed on, instead of carrying and kind of, recording the context in each of the intermediate things, we only record like flags, like a context bit field, where we say you need this, this, and this. Right.
The watch point itself, we want to be top one. The watch point itself, of course.
Yeah.
Is it on? Hey, it is. Wow. Hello. So now I can speak like normal voice.
Yeah.
So what Zoran is saying is it's two different areas. So when a dwarf expression is evaluated, when you do a watch foo, there's going to be an evaluation of the current location for foo, potentially a dwarf location expression, and then the result of that is a value, a struct value in GDB that says something like foo is thread specific, or foo is just a global that is like process specific, or it can be a local variable in the current lane, current work item. So that value will carry that information of the scope, but it won't say which lane or which thread it is bound to. But then all the way, that information is carried all the way to the watchpoint command, which then goes like, oh, it's lane specific, so I'm going to record the current lane. And then that is stored in the watchpoint object. Or if it's just thread specific, I record the current thread, so when the watchpoint triggers later, I know if the watchpoint triggered in the thread that I care about. And now it's the same for the lane. If it's specific to a lane, then is this the lane that I care about? But that is all in the CLI, the user interface that normal users use. That's not visible. It's like taken from the current context. In MI, frontends are not meant to rely on current context. So, should I stop? No. So MI commands are meant to be context independent. So the frontend should always say to which thread they're talking about, that dash thread option that Barry showed, and now the new dash lane option. So the frontend shouldn't rely on, oh, I last stopped at lane 3, so the next command will apply to lane 3. They shouldn't do that. So they should always say, because there are different ways of changing the current context. So it could be that the user changed manually the current context behind the frontend's back, so that would be bad. So the frontend should always be explicit. So that carries on to this var create as well. So we needed a way to be explicit, saying, I'm creating this var object, and I wanted to care about this particular lane. So that's why you see these explicit things in MI, and you didn't see them in the CLI.
No, I agree with that. My comment is, I do think that it needs to be explicit in the expression as well. And the reason for that is, first, I mean, you can do a the context switch from one thread to one lane to another lane. It doesn't re-evaluate the whole expression. It kind of expects it. It uses the scope and just says, well, it's there. But then we also found issues with if you have, if you have threads for multiple inferiors, not really inferiors, but kind of like heterogeneous system, like in AMD, you have threads from multiple providers effectively. And then you go to one thread, you create a variable with specific type. And then you go to another thread, you want to reuse that same variable. And then you're like, well, the variable is kind of context independent. It's kind of only dependent on the current focus, and I change focus, so it should work fine. But that's not really the case, because first, dwarf is not context independent. That was valid. Second, the type information as well in dwarf, in GDB, is bound to the target of the, where the type was found, library, and all of that. So you could actually end up with having one variable that actually references the type that is really GPU-specific type, and then you continue using it by switching a context in an expression with types from another target and try to combine them together. And how is that supposed to work? Because you actually have baked-in type in the struct value, actually type information in the struct value object. So there are these kind of things that kind of feel like all of this made sense, and the user expressions not being dependent, not really baking in the context, but being only referring to the current context made sense when we only had one provider of threads. Maybe with inferiors, we can kind of get away with, well, this is one inferior, second inferior. I don't even think that works in that scenario. But now I'm kind of raising the question, if we need to kind of bake in these things here, maybe we need to rethink the original approach and bake them actually there, because everything is really dependent on the current text. And right. even the location description, you end up, I mean, your struct value object at the end will only have the end location description. But when you evaluate the dwarf, it depends on the full context on the currently focused thread, potentially, of that thing. So, there are intermediate even results that for another thread, another thing would result in something different. So for me, it was always a question of how can we ever just say, well, it's a scope thing and we are fine. And then we discovered for watch points, we need to reverse all of that logic for the watch point itself, but it's fine for the expressions. Kind of questioning more and more, is it fine for expressions, or we just never really hit the issues because we didn't really have the heterogeneity.
So just to conclude, to answer, I think this is like, I'm agreeing with you that we need to sort this out, but I see that as orthogonal to how we expose it in MI versus CLI, because it's about that, it's about the user interface, but the issue happens whether it's implicit in the CLI, the context, or it's explicit in the CLI. It's after that point where you recorded the context. Now, what does that mean? But it's now an orthogonal question.
Yeah, I agree that it's orthogonal. I even said that when I touched on this topic, that it's orthogonal and more, maybe probably for the above, but I was just touching on it here, so.
Yes, so another question, then real quick, because we are at the end of the time slots, but then we will continue the discussion outside of
Yeah, right. Just a real quick question. So when we talk about lanes, should we think of these as a hardware concept or more of a software concept? Because when I saw the unused state, to me that's kind of taking on a hardware view of how we describe that thing. And does that differ than threads today in GDB? Because threads is really more of a it's more of a software view, at least in my mind. Like I don't need to know the core ID,
like
for instance.
here, definitely the lane is a hardware concept. That's something the hardware is really aware of. Like because we have that predication mask, that's really how it works. So we're really mapping. We're teaching the debugger about the concept of that hardware, which is kind of GPU specific concept that does extend to some degree to CPUs, but it's not as pregnant as it is on the GPU side. Okay, I think we are over time. We're not being kicked out, so okay. But I guess there's going to be some other talk after that. Thanks all, and like happy to continue the discussion, throughout the conference. Thanks.